Okay, dear students, before I start with it, let me introduce myself to D division students. I am Dr. V.V. Kulkarni, and I hope 4th C division students still remember me. Okay, so in the previous lectures, we have studied about second law of thermodynamics, the two popular statements, Kelvin-Planck statement and Clausius statement. Before to that, in the first law, we have proved that energy is a property of the system, and we have dealt this first law for both closed system as well as for open system. So similarly over here, we need to first define the second law, which is already done, Kelvin-Planck and Clausius statement, and these two statements are defined for cycle or cyclic devices. Now in this particular topic, we are going to apply the second law of thermodynamics for processes. Okay, that is a major shift from second law to entropy. So how we have defined in the previous classes that energy is a property of the system using first law statement. Now here also we are going to do the same thing, and we are going to define this entropy as a property of the system. But before going into that, let me tell you that for this particular unit, I will be referring to two different books, popular books. The first one is Eunice Sengel, as usual, and the second one is Sontag, Bornevik or Van Walen, which is popularly known as. Okay, of course, along with we require property tables, okay, while covering the numericals. So what is entropy altogether? As we have already defined it, like stated, what is entropy? Now this is very abstract property of a system which cannot be defined unless until we get into the microscopic level and analyze what is happening at the molecular structure. So in general we can explain that this particular entropy is nothing but the measure of disorderness that exists, okay, or mixed upness that exists in the process that is happening. For example, now in Belgium, all of you are observing that the roads are being digged up, right? So this, if you consider it as a process, have you watched before digging up a road, what is the structure of the road? Okay, it is quite solid. After digging up the road and again when it is filled back, can we get the same solid structure of soil or road? No, we cannot. Okay, so this is because of the disorderness that exists after the filling of that mud on the same pit is considered. So that is because of this stubbornness, which we call it as entropy, as the property. Now here we are going to consider okay. So we will be starting here with the inequality of Clausius, okay, and we end with principle of the increase of entropy, and in between there are so many phases through which the entropy has to be dealt with. So I will be trying to derive the derivations whenever they are required on the board. At the same time I explain it on the PPT. So this is how I am going to manage both the content as well as in the stipulated amount of time we can overcome the depth of this particular subject, which is vast. So the theory as well as numericals are to be covered. Followed by that, we are going to prove again here as entropy a property of the system, just like how we have proved that energy is a property of the system during our first law. So here also we are going to prove that entropy is a property of the system. and then we are going to apply this particular entropy to a pure substance, okay, which is one of the important applications of thermodynamics. And then entropy change in a reversible processes. So what we require here is a clear understanding of certain terms as applied to the second law of thermodynamics. What exactly you mean by a reversible process or irreversible process or cycles. Since you are done with cycles, now let's see the processes. Next is the thermodynamic property relations. Now in the first law again we combined some properties. So here also we are going to develop certain properties which are called as thermodynamic property relations, which are popularly called as TDS relations, okay, temperature entropy relations. And then the same entropy change we are going to apply it for solid or liquid and an ideal gas. Now this particular entropy change of solid or liquid, for this you require a specific heat concept from first law. Specific heat, that is Cv and Cp. These two applied for both solids as well as for liquids. And if you recall, this particular value of dH was nearly equal to du and was nearly equal to C, that is specific heat, of course, at T. So this we need to recall at this point of time. Okay, let's see how the things proceed. Next is the reversible polytropic process for an ideal gas. So once we know it, how this entropy is related to an ideal gas, let's apply it for a polytropic process and see the entropy change of a control mass during an irreversible process as well. And then followed by entropy generation, again one of the important concept of entropy generation, what exactly you mean by entropy generation, and then followed by principle of increase of entropy. Okay. Now here in the second law you have observed many inequalities. What are those inequalities? For example, it is stated in the second law that an irreversible cycle or an actual cycle is having less efficiency than a reversible cycle operating between the same two temperature limits. Okay. Similarly, one more inequality is that irreversible refrigerator or heat pump for that matter is having less COP than reversible refrigerator or reversible heat pump operating between the same two temperature limits. Another inequality is that always a reversible heat engine is having higher efficiency than an irreversible heat engine operating between the same two temperature limits. So these are all called as inequalities. Okay, the logical meaning behind the statement is that all they prove inequalities. Like that, one more popular inequality is the Clausius inequality, which was first developed and established by a German physicist called Clausius, who is considered as one of the founders in the thermodynamics. And he states that cyclic integral of heat is less than or is equal to 0. So what exactly you mean by delta Q by T is less than or is equal to 0? So this is a Clausius inequality. We need to prove that this Clausius inequality. Okay, let's understand some more things connected to this Clausius inequality. Now before we go further, we need to understand what exactly you mean by cyclic integral for delta Q by T. Now this delta Q is nothing but the amount of heat transfer to or from the system at the boundary temperature of T. Okay. Now for example, if I consider this as my random system under consideration, some amount of heat is added, let's say delta Q1 at a boundary temperature of T1, and if similarly another delta Q2 of heat is added to the system at a boundary temperature of T2, and then if some heat is lost delta Q3 at a boundary temperature of T3, then we can write the cyclic integral delta Q by T for this particular cycle, which consists of three different heat transfer processes, is equal to the cyclic integral of delta Q1 by T1, okay, delta Q1 by T1 plus the sign matters. Now heat is added to the system and it is positive. Here also heat is added to the system, so the sign convention is positive. The integral of delta Q2 by T2, whereas here heat is lost from the system, hence it is considered as negative, and here I am going to take the negative sign, integral of delta Q3 by T3. So this is the meaning of cyclic integral, and is written as the integration with a cycle in the middle. This we already know while defining the first law. So this is what we are going to see, and let's see how it is going to be less than or is equal to 0. Okay. So for that, let us consider this particular figure. So what it shows, this particular figure shows that from a thermal reservoir which is at a TR, thermal reservoir means by adding heat or absorbing heat, its temperature will never change. So here TR is constant. Okay. So from this thermal reservoir, delta QR, some known quantity of heat, is absorbed by this cyclic device, okay, which I call it as a reversible, hence it is called a reversible cyclic device, and this rejects certain delta Q amount of heat and thereby developing some delta W amount of work. Now since the work is developed by a reversible cycle, I call this work as delta W reversible. Okay. Similarly as delta Q reversible, delta W reversible. So obviously this particular cycle is going to exist as per Kelvin Planck statement. Okay. Exchanging heat with a single reservoir is impossible, but here it is exchanging heat as well as rejecting heat, hence it exists. It is possible rather, and it is developing a positive work, that is delta W reversible. But the amount of heat that this particular reversible cycle or cyclic device rejects is again consumed by one more system. Now the system consists of a gas, maybe in a piston cylinder arrangement, closed system, and this particular delta Q enters into this system at a temperature of T. Now here T is variable, remember that. This is a difference between this T and this TR, whereas TR is constant, hence it is called as thermal energy reservoir. Its temperature doesn't change, whereas the value of T depends on how much amount of heat that you are going to reject. Okay, so this particular T is a variable. After that, the heat is rejected, it is going to develop certain amount of work, and we are going to call this as delta W generated by the system, and hence these two are different works. Okay, so let me redraw this particular figure one more time so that you can understand the components involved into the system that is shown. Okay, so here I have taken a thermal energy reservoir which is at TR. I absorb certain amount of heat QR, delta QR, and I have a reversible cyclic device. Probably, if you consider, let it be a heat engine, okay, and let's mention this as a reversible heat engine. So this heat engine develops certain amount of work, that is delta WR, and it rejects certain amount of heat, okay, delta Q, to the system which consists of certain gas, and this gas, after the amount of heat is being added into it at a variable temperature T, expands and does certain amount of work delta W from the system. So far there is no problem in understanding the diagram. Now if at all I want to develop the Clausius inequality, here I am going to claim that applying the energy balance to the combined system. Now the combined system is what? Is the heat engine connected to the system. So this is what is my combined system. So in the combined system I have two subsystems. One is a reversible heat engine, the another one is the system having a piston cylinder arrangement, and it does certain amount of work. Now I am going to add these two works, and I say that delta amount of work generated by the two subsystems is delta WC, whereas this is the total amount of work developed by the combined system. C stands for combined work from these two. These are individual works. Clear? By the dashed line, so this is going to give the equation delta WC is equal to delta QR minus DEC. So what is this? I have just written the first law equation. So the first law equation was delta Q plus delta W is equal to DE. Okay. So what I have done here, I have just exchanged the terms. Okay. Delta Q minus delta W is equal to DEC. So this is what we have developed. The same thing I am applying here, and I will be writing that delta WC, the combined work from the combined subsystem including the system, is equal to, okay, what is that? Delta QR minus DEC, whereas DEC is the combined energy as we can see it here. Okay, you can read that, where dWc or dou WC is the total work of the combined system, which I have written here, delta WR plus delta W system, and DEC is the change in the total energy of the combined system. Okay, DEC. So this is from the first law. Let's proceed. Considering that the cyclic device is a reversible one, what best we can write for reversible cycle? Remember, in the second law, the thermodynamic temperature scale. Okay, so this particular thermodynamic temperature scale we had heard of QH by QL is equal to TH by TL, and this stands for reversible cycles only. Okay, so you must remember this particular equation, QH by QL is equal to TH by TL. So this particular equation has come from thermodynamic temperature scale, what you have learned from second law thermodynamics. So what is the next equation that we can write? Okay, this delta QR by TR, that is where you are absorbing heat at what temperature, is equal to where you are rejecting heat at what temperature. Okay, so that is the meaning of delta QR by TR is equal to delta Q by T. So here I will be writing that it is delta QR by TR, you will be able to see this, is equal to delta Q by T. Okay. Now in the next step, I am going to eliminate delta QR from the two relations. That is, here delta QR is there. So I am going to substitute what is the value of delta QR from this expression into this expression. Okay, so that is going to give you this particular equation. So what I have here is for delta QR, okay, which is equal to, it is TR transfer over here into delta Q by T. So this I am going to substitute in this expression. Okay, so after substituting, what is the expression that I am having now is TR delta Q by T minus, this will remain as it is, DEC. So this is equal to delta WC. Okay. Now since this is for a process, let's integrate this. So after integration, our equation in its integral form, okay, how best we can do the integration. Okay, so this I am going to integrate it, and this also I am going to integrate it, this also I am going to integrate it. So the integration of delta WC is what? Is WC. Now the integration of this TR delta Q by T. Remember, TR is constant, so it's taken out from the integral, and I have only delta Q by T. I would like to keep it as it is, delta Q by T minus integral of DEC. Integral of DEC is 0. The reason is energy is a property of a system, and the integral of any property is 0. So here you need to recall this. Integral of say dV is 0. Integral of say dE is 0. This is what we have already learned in the first unit. Okay. So based on that, we can write here that the integral of DEC is 0, and hence it is eliminated. I am going to write only this particular equation. This is what is shown over here. I have WC is equal to TR cyclic integral of delta Q by T. Okay, so let's move. What is the outcome of this particular equation? Since I am using the cyclic integral everywhere, let me use the cyclic integral of this. What this suggests? Basically, if you look into this, okay, dashed line especially. Now this particular dashed line says that we are exchanging heat with a single reservoir, and we are developing net amount of work, that is delta WC, which is not possible as per second law of thermodynamics, Kelvin Planck. Okay, we are exchanging heat with single reservoir, and if I consider this as a combined cycle, that is system and cyclic device, this is cyclic device and this is system, and together if I consider, I am getting only work, so there is no rejection of heat. So it is not possible, it is impossible to construct a device which exchanges heat with a single reservoir and develop some amount of work. So when this particular equation is not possible, meaning what? Meaning is WC doesn't exist, okay, and hence is not a positive quantity. Am I clear? Hence it can concluded that WC cannot be a work output, okay, and thus is cannot be a positive quantity. When this is not a positive quantity, okay, then obviously we have no choices here. This is 0, this side is a positive, and this side we have negative. So this cannot be a positive quantity. So either it is 0 or negative. So obviously this doesn't exist, and hence is a negative. Considering that TR is the thermodynamic temperature and thus a positive quantity, we must have, okay, now let's see. If I take down over here, WC by TR is equal to cyclic integral of delta Q by T. This cannot be a positive quantity, so it is negative, divided by TR is a positive quantity because it's a constant, positive, is equal to cyclic integral of delta Q by T. Now what is negative by positive? Is negative, okay, and is equal to cyclic integral of delta Q by T. So if it is not positive, either we have a choice that it is positive or negative. Okay, so when I readjust it and I rewrite it, then I'm going to get that the cyclic integral of delta Q by T is less than, that is for negative, or is equal to, that is for 0. Okay, this is what we have achieved. This is the proof. Clausius inequality, or popularly called as inequality of Clausius. Okay. Proceeding further, we can now claim that the cyclic integral of delta Q by T is less than or is equal to 0. So here you must understand why the signs are selected. WC cannot be a positive quantity, hence it is either negative or 0. TR is positive, so negative by positive is negative. If I take negative, then the cyclic integral of delta T is going to be less than. Okay, so I have taken less than, or if it is equal to, then it is 0, hence the proof. Okay. Now here we can observe one more thing, that in the reversed case, okay, since I have taken a reversed cyclic device or reversible cyclic device, that means all the processes can be reversed by changing the direction. Okay, all the quantities have same magnitude but the opposite direction. Claiming that, therefore, the work which was or which could not be positive in the earlier case now cannot be a negative quantity in the reversed case. Okay, if I reverse the direction of the combined system, that is a dashed line, the components inside that, if I reverse that, then whatever WC that we got, which cannot be an output or which cannot be a positive quantity, now cannot be a negative quantity in the reversed case. Then what we have? It thus follows that WC is equal to 0. Okay, it thus follows that WC in the first case is not a positive quantity, and in the reversed case it cannot be a negative quantity. So it says that WC is equal to 0. So when this WC is equal to 0, what is the condition applied? The condition is that it is for WC is equal to 0 for internally reversible processes. So when this WC is equal to 0 in the equation, obviously we have 0 over here by TR is equal to cyclic integral of delta Q by T, or rearranging this, we can write that cyclic integral of delta Q by T is equal to 0 for this internally reversible processes. Okay. So this is the outcome that we can get it from this particular derivation. So cyclic integral of delta Q by T is equal to 0. Clear? So let's move forward. Okay. So finally, what is the summary? So we can take that it can be concluded that from this particular expression of Clausius inequality, that the equality holds good for reversible cycles. That means if I split this equation into two, then I can write that cyclic integral of delta Q by T is equal to 0 for all reversible processes or cycles. Okay, whereas always the cyclic integral of delta Q by T, okay, is less than 0 for all irreversible cycles or processes. Okay. The next outcome is that we know that the cyclic integral of any property is 0, okay, which are already written on the top. Cyclic integral of any property is 0. So can we make out something and claim that this particular cyclic integral, okay, if it is 0, then what is that quantity is called as? If the cyclic integral of any property is 0, then that particular quantity, or can say this, a quantity whose cyclic integral is 0 depends on the state and not on the process path, and thus it is a property. Hence we can claim that entropy is a property of the system. Therefore the quantity delta Q by T, especially for the reversible cases, okay, is, or it must represent a property in the differential form. So Clausius realized this and he has discovered a new thermodynamic property, and he chose the name to this property as entropy. So this is in the beginning that we are going to define entropy. Thus it is cyclic integral of delta Q by T and is equal to 0 for reversible cycles and is always less for irreversible cycles. And he designated S, the symbol for that, and then he says that for so given the value as capital S for entropy, and based on that we can write small s for specific entropy, as entropy is an extensive property. Okay, so let's see the equation, or in its equational form, ds is delta Q by T. Now one important thing here is we need to always write, if this S is equal, then internal reversible has to reflect, otherwise we are missing an important component of defining entropy. When is the entropy change of a system during a process? Now, to complete a cycle, it can happen through different processes. So what is the entropy change of a system during a process, which can be determined by integrating this above equation. Okay, if we integrate this particular equation, we are going to get the integral form as delta S equal to S2 minus S1 from process 1 to 2 integral delta Q by T internally reversible case, and it is expressed in kilojoule per Kelvin. Okay, so this equation, or sometimes it is written as delta S also, or sometimes it is written as ds also, both are okay, which is equal to, okay, cyclic integral from delta Q by T from process 1 to 2, and if I write it, it's going to be S2 minus S. So that is what is written over here, where S means it is integral Q to 1, or the same thing can be elaborated further. So let's take up a special case here, internally reversible but isothermal heat transfer process. Now again, in second law we have considered this isothermal process. The meaning of isothermal means at constant temperature. So how this entropy behaves for a constant temperature or an isothermal process where heat transfer is considered. So let's see a special case with a small numerical. Now this change in entropy can be written for internally reversible. Obviously this delta S is equal to delta Q by T for internal reversible case, and for isothermal heat transfer process, isothermal means the temperature will remain constant, and hence T comes out of that, and we have only integral 1 to 2 delta Q internally reversible process. So let me write that once again so that we can use it for further case. The change in entropy can be written as the integral from 1 to 2 delta Q by T. The moment I write delta Q by T, it has to be for an internally reversible process. So for now, considering an isothermal process where temperature remains constant. So in this particular case, the equation changes to, okay, I'm going to take this t out, so it is 1 by t integral from 1 to 2 delta q, okay. So the same thing is written, or you can write finally that heat transfer from 1 to 2 divided by T, okay, where T is constant, isothermal. So this is the change in entropy for a given special case, internally reversible isothermal heat transfer process. So let's take up one small example. What is that? I'll read the statement. A piston cylinder device contains a liquid vapor mixture water at 300 Kelvin. During a constant pressure process, 750 kilojoule of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this particular process. Okay, so here we are going to use this simple equation, and let's see how we can calculate the change in entropy for a special case of internally reversible isothermal process. Now this is the diagram. We have a piston cylinder arrangement in which we have the system. Now that system is nothing but what? A liquid vapor mixture. So we have some liquid vapor mixture which is at 300 Kelvin. Now during a constant pressure process, so this cylinder is having a constant mass, some 750 kilojoule of heat is transferred to the water. As a result of this, whatever the liquid portion was there, now that's converted into vapor. That's what he says. Okay, liquid in the cylinder vaporizes after the heat of 750 kilojoule is added. Determine the entropy change. Now to get this entropy change, what we require? We require what is the initial entropy and what is the final entropy. Now since here it is taking place at constant temperature, we know the temperature, we know what is the amount of heat transferred. By using this particular equation, we can very well find what is the change in entropy. Okay, so let's see that. Solution. In the solution, the system undergoes an isothermal process. This is what we have identified, and thus the entropy change can be determined directly from the above equation to be, okay, the delta S of the system, which is nothing but Q by T. So Q is 750 kilojoule and this is 300 Kelvin. Straight away we can get the value as 2.5. So very simple direct solution. But we need to understand that we have some limitation in applying this particular integral delta Q by T equal to change unless until we have an internally reversible process. Only in case of an isothermal process where temperature remains constant, we can apply this particular equation, which is in the form of delta S equal to 2 by T. Okay. Now, what is the significance of this Clausius inequality? What we have understood so far? What exactly you meant by cyclic integral of delta Q by T is less than or is equal to 0? Where again, emphasis is that equality sign holds good for a reversible cycles only, and less than, which we call it as inequality, is applicable for all irreversible cycles. So now at this point of time it becomes very essential to note what is the significance of this inequality of Clausius. Now it can be explained with the help of a simple power plant, steam power plant. Of course, this particular steam power plant we have already considered during our first law for open system, okay, power plant, which consists of 4 important components as the boiler, turbine, condenser and a pump. But here the conditions are different. The condition is that steam enters the boiler, okay, at state 1 as a saturated liquid. So at state 1 what we have here, if I write the phases of steam at different locations of a power plant, then at state 1 we have saturated liquid, okay, which is nothing but subscript as F. At what temperature or pressure? At 0.7 megapascal. So this is at the rate of 0.7 megapascal. So this particular saturated liquid enters the boiler, absorb some amount of heat, and then get converted in the form of saturated vapor. So at state 2 what we have is, at state 2 we have saturated vapor. So phase is changing here, from liquid it is changing to vapor. So the subscript what we are going to use is G. What is the pressure? But at constant pressure, 0.7 megapascal. You can see that it enters the boiler at 0.7 megapascal and it leaves the boiler at 0.7 megapascal. So we are supplying heat at constant pressure. That is the catch over here. After that, the steam enters into the turbine. Okay, enters into a steam turbine. Now this turbine also we have seen in first law applied to open system, and we are well versed with handling the equations as applied to all these components. Remember SFEE equations, we already solved SFEE equations, and then this particular steam enters at 0.7 megapascal into a steam turbine. So in the turbine it converts all its energy, steam energy or enthalpy, into useful work as W, and then it leaves the turbine at state 3 at 90% quality. And what is the pressure? The pressure is 15 kilopascal. So we need to again quote what are the conditions at state 3. So at state 3 we have 90% quality. Quality means the value of X is 0.9, okay, and we have pressure at 15 kilopascal. So the pressure drastically drops from 0.7 megapascal to 15 kilopascal, and the drop in pressure is being used in terms of developing the work. The pressure enthalpy is converted into useful work. From there, at state 3, after exiting from the turbine, it enters into a condenser. So again, condenser is a type of heat exchanger where heat is being lost from the steam and the condensate is taken from the pump to circulate it back to the boiler. At what condition? At state 4. So again, at state 4, what are the parameters we have? At state point 4, the condensate enters at 10% quality and 15 kilopascal. So here the quality is 10%. Obviously it is moving more towards saturated liquid from saturated vapor. So the value of X is being 0.1, okay, and at a pressure of again 15 kilopascal. Okay. And then it enters the pump. The pump circulates all this at state 4 back to boiler, and the cycle repeats. So here in the cycle there are 4 different components. How to execute this inequality of clauses. Now the question is, does this cycle satisfy the inequality of clauses? This is very, very important. Through this only we are going to explain the significance of inequality of clauses. Okay, if this inequality of clauses, say cyclic integral of delta Q by T is equal to 0, then all these processes or cycle is for a reversible one. If it is less than 0, then obviously this is a reversible cycle. Okay, so let's take out that. Let's analyze. So here we can say that heat is transferred in 2 places. What are those? One, in the boiler, heat is supplied, so which is between 1 to 2 state. So here at between 1 to 2 state, heat is supplied from 1 to 2. Some known quantity, I don't know what exactly is. If I know the total mass, then it would be capital Q 1 to 2. If not, then I want to assume that for 1 kg of steam, how much amount of heat is to be transferred. So in that case, I am going to consider this as small 1 to 2 is how much. So this is the amount of heat that is supplied. Since heat is supplied, So this is going to be a positive quantity. Okay, heat is supplied to the system in the boiler, so this is going to be a positive quantity. Another is boiler. So another is condenser. In the condenser, heat is being rejected. So this is taking place between state 3 and 4. That means somewhere here. So in the state between 3 to 4, certain amount of heat, that is from 3 to 4, heat is being lost from the system, hence it is going to be negative. Clear? Between 3 and 4, heat transfer between 3 and 4 for unit mass of steam, the value is going to be Q. I don't know the quantity, so it is going to be negative. Okay. Then moving next, I can write the Clausius inequality, which is mentioned as cyclic integral delta Q by T. How to write it for this particular diagram is shown over here. So let me write that equation once again. So what I am going to write here, the cyclic integral of delta Q by T is equal to, now I am going to write it for two different components, one for boiler and one for condenser. So this cyclic integral of delta Q by T is first for the boiler plus, okay, plus the another one is for the condenser. So again, the cyclic integral of delta Q by T for the condenser. B stands for boiler and C stands for condenser. At these two states, what are the components that I know? Okay, since the temperature remains constant in both the boiler and condenser, okay, nowhere I have mentioned the temperature. So here also it is at constant temperature and here also it is at constant temperature. So heat addition is at constant temperature, heat rejection is at constant temperature. So this may be integrated as follows. Okay, so how we can write it in the integral form? Obviously the value of T is going to be constant, so I am going to take T, but since T is at state 1, so I have mentioned here as T1. So here from this equation I will be taking integral 1 by T1 and I am going to write here it as integral delta Q. Okay, so which is from state 1 to 2. So this is from state 1 to 2, this is from state 3 to 4. So let's continue the same thing, and this is for the boiler plus for the condenser is again it is at T3, so I will be taking this at T3 and I will be continuing from 3 to 4 delta Q in the condenser. Let me keep this positive sign as it is unless until I get its corresponding quantity in negative. Let's continue with a positive sign. So for that reason I have kept this particular positive sign. So when you equate it, the amount of heat transfers, what I have is the amount of heat, that is Q straight away available from 1 to 2 at T1, okay, 1 to 2 at T1, plus the amount of heat that is available Q 3 to 4. So this is in the boiler and this is in the condenser, which is at T3. Let's find out all these properties from property tables. Okay, what are those? For a unit kg of mass of working fluid, we can reduce that equation in the simplest form as already told. I don't know the mass, so what I am going to do is, for simplicity, I assume that it is for unit kg of mass. So this particular equation reduces to Q1 to 2 at T1, okay, plus Q3 to 4 at T3. So finding the properties from the property tables, Q1 to 2. How to evaluate Q1 to 2? Now we have to apply SFEE to boiler as well as SFEE to condenser, both are heat exchangers, and develop the equation. So here I have written Q1 to 2 is H2 minus H1. Rest all potential energy, kinetic energy are neglected, hence they are omitted from the SFEE for boiler. So what I have written here is H2 minus H1. So this particular H2 minus H1 yields. So we have to find these two from the property tables. What is H2? H2 is available at 0.7 megapascal. What is the corresponding value of Hg? So since it is saturated vapor, the phase of steam, the moment it comes out of the boiler at state 2, here H2 is going to be Hg at what? So let me elaborate this. Hg at 0.7 megapascal minus, we have H1 here. So H1 is entering the boiler, which is saturated liquid. So obviously this is H1 in the form of F, liquid, at 0.7 megapascal. So this you need to get it from the property tables and verify that you follow the same numbers as what I have written there. So go to pressure table, 0.7 megapascal, and at 0.7 megapascal, okay, the corresponding temperatures, T1, that is saturation temperature, is 164.97, which is correct. So I'll be taking the values of T1, what shall I write? T1 is 164.97 degree Celsius, and T3, which is at quality and 15 kilopascal. So I have to refer from the table. At 15 kilopascal, the corresponding temperature, saturation temperature, is 53.97 degree Celsius, whereas the corresponding enthalpy, okay, so I have to refer to Hg at 0.7 megapascal, sorry, 0.7, yeah, megapascal. The value of H2 is Hg, that is 10th, so at 0.710, 2763, 2066, the value 9 HFG. So saturated vapor, so the value is 2763.5, 2763.5, this minus HF. So at 0.7 again, get the value of HF, which is column number 8, which is 684.28, 684.28. So the difference of 2763 and this will give you 2066.3 kilojoules per kg. This is important since I am working for 1 kg, so the values are this. So T1 and T3. Similarly, for Q3 to 4, where it enters at 3 and leaves at 4, so the difference is that we are going to have H4 minus H3. So it is H4. What is the state at H4? H4 is a condensate, 10% quality and 15 kilopascal. So go to HF at a temperature, at a pressure of 15 kilopascal, which is 463. At 15 kilopascal, find the value. At 15 kilopascal, the value of HF okay, we have this quality also. So this HF, after writing, is H4 minus H3, find them separately. So this HF is equal to what? It is HF plus X at state point 4 into HFG. So this HF you have to calculate it as 0.15 kilopascal. Okay, the value of HF at 15 kilopascal is how much? Is 225.94. plus what is the dryness fraction? Dryness fraction is 10%. So at 0.4 it is 1 and H of G. Hg is 2373.1. So it is 2373.1. So calculate the value of H4. So this H4 is going to be 463. So this I would write here as 463.4 okay, kilojoule per kg. Similarly, we can get the value of H3 get the value of H3 at H3. How to calculate is again HF plus X3 H of G, all the values at 15 kilopascal. So go to pressure table, find the value. So at HF again this will remain same, 225.94. only change is that at state 3 we have dryness fraction 90%. So this is 0.9 and this value will remain as it is, 2373.4. So after calculating you get this to be higher because the dryness fraction is more and hence its enthalpy content is higher. So this is 2361.8. This is 2361.8 kilojoule per kg. Okay. So after substitution we get Q3 to 4 as negative, okay, because lower minus higher value. So it is minus 1898. So minus 1898.8 kilojoule per kg. Therefore, after substituting in the equation, what we get is delta Q by T, cyclic integral of delta Q by T for this particular cycle is 1 by T1. T1 has to be converted into absolute values. So here I have 164.97 plus 273, so that gets converted into Kelvin over here, this part. Now the plus sign is now replaced with minus sign, okay. So this is a change here. For this particular term we need to write down the remaining value, minus 1891 divided by 53.97 degrees Celsius, again need to be converted, hence we get it as negative. So what this indicates, the negative sign, cyclic integral of delta Q by T is negative. That means it is for an irreversible process. Okay. So we'll stop here and we'll take up the remaining part, that is entropy as a property of the system, in the next class.